Should be 2, right? I think this is, is it 1? Hi everyone. So last time we talked about solutions. We just continue this today. So I told you about water. I told you about the polarity of water, right? Which is due to the oxygen, which wants to get the electrons, the hydrogen, which can give the electrons. So they will form a dipole and a polar molecule. And this polar molecule can dissolve other compounds, like solid compounds. Oh, okay. Yeah, this is really bad. I think there's still some problem. Anyway, let's continue like this. So we talked first about dissolution of salts, where the water, because it has these two ends, like one negative, one positive end, it can kind of build up these hydration shells around these ions, and it can dissolve them, which means that it's like favorable for the system to go into this dissolved state rather than staying separate, right? This has energetic reasons and maybe also like entropic reasons, as we discussed last time. So different solids, they have different solubility. There are some solids, even though they are ionic, they will not go into solution, like silver chloride. So you would then basically need to heat it up a lot to get it dissolved. And there are some solids, like sodium chloride, which immediately go into solution, right? So there is something going on there about this process, which is not like trivial to understand. And then we talked also about dissolution of non-ionic substances like molecules, polar molecules which can dissolve, and polar molecules which usually cannot. We talked about conductivity, so that ions in solution, they form an electrolyte, and this electrolyte can conduct electric current. Water itself would not be an electric conductor. You need these ions to conduct electricity. And then we categorize these different types of electrolytes: strong, weak, and non-electrolytes. Strong electrolytes, which are those which dissociate completely into their ions. They produce a lot of ions which can conduct current. We have weak electrolytes which conduct only a small current in the aqueous solutions. And we have the non-electrolytes which do not permit any current to flow. Okay, and we also realized that the conductivity depends on the number of ions, and different compounds will produce a different number of ions per formula unit, right? For example, calcium fluoride will produce 3 ions per formula unit, while sodium fluoride produces only 2, right? So if they both dissociate completely, then the conductivity of calcium fluoride would be higher than for sodium chloride, right? Simply because we produce more ions per formula unit, right? So that is something we importantly realized last time also. We also discussed about acids, which are those which can donate protons, and then by that they can produce ionic solutions, electrolytes. Strong acids are those which completely dissociate, so all of these acid molecules will just convert into these anions and cations and protons. Weak acid are those where some of them stay undissociated, so similar to weak electrolytes, which are staying undissociated to some degree. So acetic acid was some example for a weak acid, where some of those molecules just remain as acetic acid, and some convert to the acetate anion. And similarly, we could also define a weak base as something which is not entirely reacting and accepting protons. Okay, I just have to find a point where we were. I think this one we also discussed. So non-electrolytes are those which do not dissociate into ions. And then we talked shortly about the molarity, which is the concentration. So if I want to summarize one more time, let's use this luxurious chalk here. I'm not sure if I'm allowed to use this one, but I will just use it. I really like this. Okay, so we have concentration, which is the mole number over the volume. This is the mole number of the solute. And this is the volume of the solution. It's not the volume of the solvent, it's the volume of the combined solution. And just as a reminder, our important equations that we always used. As from before. So this kind of sums up the most important equations that we discussed so far. So combining these together with stoichiometry, you can almost solve any problem for chemical reactions. And then we did a couple of exercises here for this as well. And I think we did all of this. To find the point. I think we didn't do this one, right? Yeah, I think. No, we didn't do all of this. Sorry, I just need to find. Can somebody tell me what was the point until? I think we came until this point. We didn't do this one also, right? Yeah, maybe this one was the last, right? This was the last, right? Now I remember also we had this here with the moles times the number of ions per formula unit. Okay, so let's continue from here. So we do one more example. A typical blood serum is about 0.14 molar sodium chloride, right? Remember the concentration is measured in mole per liter, which is abbreviated as a molar. What volume of blood contains 1 milligram of sodium chloride? Okay, so how do we approach this one? We want to find the volume of blood containing 1 milligram of sodium chloride, and we know the concentration. We know the mass. Okay, so we just have to use these equations that we have there. What information do we need to find the volume of blood containing 1 milligram of sodium chloride? Well, we need to first know the moles, right? Always it's good to go via the molar number. Once we know the molar number, then we can easily use molar mass to convert this into a mass, right? So essentially we want to know the moles of sodium chloride in 1 milligram. And so what do we do? We calculate first the moles of sodium chloride per 1 milligram. That would be 1.7 times 10 to the power of minus 5 mole. That's just using this equation there. And once we have this number, we know that 0.14 molar sodium chloride contains, so what more volume of this concentration contains 1 milligram? So there is some volume, let's say it's V. When we multiply with the molarity, it yields 1.7 times 10 to the power of minus 5 mole. Okay, so it's V times this concentration. So V times this concentration. Here's the molar number. The molar number we have, the concentration we have. So we just need to solve this for the volume, which is then 0.12 milliliter. 0.12 milliliter of blood contains 1.7 times 10 to the power minus 5 mole of sodium chloride, or 1 milligram of sodium chloride. Yeah. So when you prepare solutions, then typically there's something which is called a standard solution. This is a solution whose concentration is accurately known, and you use this one to benchmark, to upgrade to other concentrations. So in order to prepare the standard solution, you place a weighted amount of the solid into a volumetric flask. You add a small amount of water. You dissolve it first, and then you add more water until the line of the mark of the flask. And you do that several times. So this is how you can prepare a precise concentration. So you have the weighted amount of solid there, you put a little bit of water first, you make sure it's completely mixed, and then you bring it up until the point where this meniscus is at the bottom of that marked line, right? And then you have your solution which has a very well-defined concentration, and you can use that for bringing this to other concentrations or using this for your experiment. So one example here, to analyze the alcohol content of a certain wine, a chemist needs 1 liter of an aqueous 0.2 molar potassium dichromate solution. So the volume is 1 liter, the concentration 0.200 liter. Okay. How much solid potassium dichromate must be weighed out to make the solution? So, as you know, we can use this equation to get N, right? And from N we can always come to M using that equation, right? So this is the kind of workflow to get this done. So we start with the this first equation. We multiply the volume with the concentration to get the mole number, 0.2 mole. And now we just multiply this by the molar mass here to get the mass, which is 58.8 gram. So in order to prepare 1 liter of this solution, you have to weight this amount, put it into the flask, dissolve it in water, and then bring up the water to 1 liter. Yeah. So this is how you can prepare then 0.2 molar solution of potassium dichromate. And again, be careful with the significant figures, right? If you really want to have 3 significant figures in the concentration, you also need to weight the mass with 3 significant figures, right? So that's, you need to make sure that this is accurate enough, that you can, precise enough that you can get that number. And also the flask should have the accuracy, the precision to measure 3 significant figures in the volume, right? Okay, and then once you have the standard solution, you can also easily dilute it. So the idea here is that you have this concentrated solution, a certain volume of that, and then you add water to it to bring it to a dilute solution. And the important point here is that the moles of the solid will always stay the same, right? You only add water to it. So the moles before and after will be the same. So let's say you have here solution. This is the concentrated solution. And then you add some water here. Then the mole number of this concentrated solution of the solute, its name is Cn solute concentrated, will be exactly the same as the total number of the dilute one. So we can equalize those two. We can say N solute concentrated equals N solute dilute. And as you know, N we can always write it as a concentration times the volume. So we have the concentration of the concentrated case times the volume of concentrated case. And this has to equal the dilute concentration times the dilute volume, right? So with this simple thing, then usually you know the concentration, you know the volume before, and you know what is your concentration that you want to get to, right? So you can solve this for the volume, and you can know how much volume of the dilute solution you need to prepare. Yeah. So this is usually the way that you can do this. Typically, then you can also use this pipette, which you can use for accurate measurement or transfer of a given volume of solution. So in order to do this, let's do some example. So what is the volume of a 16 molar sulfuric acid solution that we have to use to prepare 1.5 liter of a 0.1 molar sulfuric acid solution? So in this case, we know the final volume. We know the dilute volume that we want. This dilute volume is 1.5 liter. So this one is known. The concentration, the final concentration is 0.1 molar. This is known. The dilute concentration, concentrated is 16 molar. And this is the question mark, right? So we can just solve for this one. And then we have the answer. So we take in this case they do it in 2 steps. So they first multiply their volume here with that concentration. They get 0.15 mole. And then we can take this one and we can divide it by the concentration. And then here, 1.5 mole divided by 60 mole per liter, and then we get the final volume, which is 9.4 milliliter, right? Okay, so if we want to do this in practice, that means we need to add to the solution. The concentrated solution is 9.4. So we would put 9.4 milliliter of that concentrated solution into the flask, and then we would fill it up until the 1.5 liter mass mark, right, of the flask. Okay, so this is this equation which I just talked about. Okay, you can do more exercises again. So let's do a join-in. 500 milliliter of a 1 molar solution of sodium chloride is diluted to 750 milliliter. What happens to the number of moles of sodium chloride in the solution? A, it decreases. B, it increases. It's same or not enough information provided. So who thinks it's A, B, C, D? That's what I just explained, right? Then the molecules are not changing. You're just adding other molecules there, right? So the molecules of the solute are still there. The number is the same, right? So, okay, so today we want to talk about these different reactions more that can happen in the solution. So we have precipitation reactions, or we could also call this dissolution reactions. And we already discussed this a little bit, right? When we put a solid into the water, like a crystal, like sodium chloride, it can dissolve. This is actually a chemical reaction. We also talked shortly about acid-base reactions, right? where we have proton dissociating or associating with a molecule from water. And also we have oxidation reduction reactions, which we didn't discuss so far, but we will do this today. So precipitation reactions is if we have something which forms a solid in the solution. Yeah. So one example would be we put a solid into a solution and it cannot be totally dissolved, and there's a precipitate left, right? This is what we call precipitate. So we have something here. Call this the precipitate. And we have the solution here. And as I told you last time, there's a constant process going on of molecules dissolving and then again precipitating. And on average, there will be some precipitate left. But if we use, for example, sodium chloride, there's basically no precipitate left because the reaction is lying on the product side, so it's a complete reaction almost. But for all the other, for many other salts or solids, there will be some kind of process going on, constant process going on. So this is the precipitation. And this is the dissolution. Now this is just one example. We could also, for example, take two solutions, and then sometimes the precipitate can form from that. So you could imagine you have like a solution of a cation A and anion B, and you have another solution which is a cation C and anion D. And this solution is well dissolvable. It has a high solubility. This one has a high solubility. But once you combine them, then A and D really likes to form a solid. They have a strong tendency to form a solid. So you might form some solid AD here. And in solution, maybe you are left with B minus and C plus. Right? So when you combine solutions, also precipitates can form. Example here, you add yellow aqueous potassium chromate to a colorless barium nitrate solution. So in this case, it will form barium chromate. Okay, so and this one would be basically barium chromate. And then before you had barium nitrate. Okay, so this was here, barium and nitrate. And this was potassium chromate. Okay, 2, 1 minus, probably. Chromate, no, CrO4, right? CrO4 minus. Okay, so the idea is you combine solutions and maybe they will have some components which together will form a precipitate. That can also happen, right? So this is this, one more time, visualize. The two solutions separately are perfectly miscible. Solubility is high, but once you combine them, you start to form this precipitation product. You can write down this reaction. So here you have this potassium chromate, barium nitrate, and somehow you combine them, you form products. You can like write all these different ions here, which are in solution, because all of them are in solution, and somehow you're forming products. And then if you see this here, you form this precipitate, right? combine them together, which is barium chromate. You can see this precipitate on the ground of the solution. Okay, so this already tells us that we really need some kind of better understanding of solubility, right? And as I told you before, it's not really simple. Like if we want to understand the physics of that, there are many factors that play in. But luckily, there are a couple of simple rules that we can use to get some kind of rough estimate if something is soluble or not. Yeah, to be honest, I think I don't want you to memorize all of that. I think such rules are always there. There are too many exceptions. So, but anyway, let's just roughly go over them to keep some in mind. So, nitrate salts are usually soluble. When we have alkali metal ions involved, or ammonium, they are usually soluble. This is quite useful rule, right? Because we have many salts with alkali ions. So it's quite good to know that they generally are soluble. And well, that's quite interesting also, like physically, why that is, but we'll discuss this not today. That's probably actually even ongoing research why that is the case. And third one, most chloride, bromide, and iodide salts are also soluble. But there are some exceptions, which is involving silver, lead, and mercury, right? As you know, we discussed silver chloride has a very low solubility. It will only give a couple of these ions in solution. Rest just remains as a precipitate. Sulfate salts are usually soluble. But again, there are exceptions, right? So now you realize why I don't like these rules. I mean, there are just too many exceptions. Like, this is not something we can generally say. But I think the first two rules are quite good, quite important. Then most hydroxides are slightly soluble. Important soluble hydroxides are sodium hydroxide and potassium hydroxide. But the compounds barium, strontium, and calcium hydroxide are marginally soluble. Right? And most sulfate, carbonate, chromate, phosphate are only slightly soluble, except for those containing cations in rule 2. Okay? So I think the most important are rules 1 and 2. All the others have so many exceptions, so I'm not sure if it really makes sense to learn them. Okay, but using these rules, predict what will happen when the following pair of solution is mixed. Potassium nitrate and barium chloride. Okay, so what we just said is that potassium nitrate is involving potassium and nitrate. And we said potassium and nitrate both are very soluble. They will form soluble compounds. So we can say with relatively for sure that this will be in solution. And then we have barium chloride. We have again like some earth alkali metal, which is has a high tendency to go in solution, and halogenides as well. So this will also go into solution. And now we combine this one. The question is, what are the possible products that form for precipitation? Well, barium and chloride apparently was in solution, so barium could, however, combine with a nitrate, or potassium could combine with chloride. Well, potassium chloride, we already know that this should be soluble, right? But how about the barium nitride? So nitrate ions are also soluble in water, as we know. So we predict from the rules that they are all soluble in solution, and we will form no precipitate. One other example for joining, lead nitrate reacts with sodium chloride in aqueous solution to form a precipitate. What is the next ionic equation for this reaction? Okay, so who thinks is A, B, C, D? Okay, mostly C. So what are the possible products that can form? So as we said, the solutions themselves, they're already solutions, so they are well soluble. So we can combine the cation of solution 1 with the anion of solution 2. So we could combine, for example, lead with chloride. That would be this here. And we could also combine sodium with nitrate. That would be this here, right? So these are the two possible products we can form. However, we know that sodium is a alkali metal. They will always form soluble solutions. So as well as nitrate as well. So this will not be probably happy. So this is much more likely the answer, right? So according to the simple solubility rule, we can say that C should be the answer. Aqueous solutions of sodium sulfate and copper chloride are mixed. Which statement is correct? A, both sodium chloride and copper sulfide will precipitate from the solution. B, no precipitate will form. C, only copper sulfide will precipitate from the solution, or only sodium chloride will precipitate from the solution. Okay, so who thinks is A, B, C, D? Okay, I give you just 10 seconds. That's maybe too fast. Okay, so who thinks A, B, C, D? Okay, yeah, looks good. So sodium chloride, of course, is soluble, right? No precipitate would be in principle possible, but we also know that sulfides are usually not that soluble. I will probably not take this example for short test or exam because I don't want you to remember all these exceptions. But anyway, from the table, if we look at that now, we can see that sulfide probably will precipitate. Right? Okay, another one. Aqueous solution of barium nitrate reacts with aqueous solution of sodium sulfate. Identify the solid and indicate the coefficient in the balanced equation. Okay, so who thinks is A, B, C, D, E? Oh, what happened? So with coefficient, they mean, I think, the stoichiometric coefficient in front of this solid. So if you write down the chemical equation for that reaction, then there would be some coefficient in front of that solid, maybe. So that's the question here. So what should be the salt that is formed? Sorry, couldn't hear anything. Barium or sodium? barium, right? Sodium is soluble, we know that. So B or D is the question, right? And so we need to write down the chemical equation. Okay? So if we write down the full equation, then we have barium, we have nitrate, then we have sodium, and we have sulfate. And all of this is in solution. Let's put the AQ here. And this reacts to barium sulfate. And you can see that it's already well balanced. We have 1, 1, 1, so it's well balanced. And then we have again the 2 sodium plus 2 nitrate, which are still in the solution. So typically what we do is we ignore this one because it's on both sides of the equation, right? So we can just write the equation like this. So in fact, it's 1, right? So B is the right answer. Okay. So this is what they are talking about here. So the formula equation has like all the ions in there. Sorry, no, the formula, I was confused the two. The complete ionic equation has all the reactions and products that are strong electrodes, and the formula has only the participating one. So this would be the formula equation. And the net ionic one is including only those who participate. So let's do example here. Okay, formula equation, we don't put the ions at all, we put only the compounds. The ionic equation has all the ions which go into solution, so that was what we had before. And then the net ionic equation is the one which has only the participating ions. Okay, these are the three. Yeah. Formula, complete ionic, and net. So usually the net ionic is enough, right? Because all these other ions, we call them usually spectators. They just observe, they are just there to observe the reaction. They are not doing anything with the reaction. They might influence a little bit, but not too much. So they are mostly spectators. Okay. So this is a general problem-solving strategy when you have these kind of solutions and you want to solve some problems. So the first is you identify the species which are in the combined solution, and then you determine what reactions can occur. So we did many join-ins for that. Then you write the balanced net ionic equation like this one here for the reaction. Then you calculate the moles of reactant and then determine which one is limiting. And from this you can calculate how much product is formed, and you can convert this to gram or other units. So if you want to know, you put two solutions together and you want to know how much product is formed, this would be exactly the way to do this, right? Get the net ionic equation, identify what is limiting, because you might have more barium than sulfur, right? They don't need to be exactly balanced. So you could, for example, use the same ion from another solution and you could combine them. You could take like barium chloride solution and combine it with barium chloride. Well, you could use something where the cation is the same in both cases, or the anion is the same in both cases, right? And in that case, you could like determine the limiting reactant in this case, and then convert to the product mass. Okay, so one example, you have sodium sulfate and lead nitrate, they are mixed, and you precipitate lead sulfate. Calculate the mass that is formed. If you have 1.25 liter of that 0.05 mole of molar lead nitrate solution and 2 liters of that molar sodium sulfate solution. So from this you can immediately see, because you know all these equations, right? So C times V gives you always N. So you can just multiply the volume, the concentration with the volume, which are both given. So you're essentially given the molar number of those two. Okay, so let's do step by step. We write down the net ionic equation. So lead sulfate is formed. So we write down lead 2 plus sulfate 2 minus reacts to lead sulfate. What information do we need? Well, we need the limiting reactant, and for that we need the moles, right, as we know. So how to get there? The balanced net equation we already have. So we calculate the moles by multiplying the volume with the concentrations. And you realize that you have different amounts of lead and sulfate. So what is the limiting reactant for the precipitation reaction? Sulfate, right? It has less moles. So in the reaction we need the same amount of lead and sulfate. So the one which has less will form less product overall. So it's limiting us to 0.05 mole of product, right? So we will form 0.05 mole of the product, and we can convert it into a mass with the molar mass, and then we get 15.2 grams. Yeah, so this is the strategy we can use to determine how much precipitate we will form. By the way, you could also do it in the other way around, in principle. Let's say you want to know the concentration. Then you can put them together, and you can kind of remove the liquid, and you measure the mass of the precipitate. Right? Then you have the mass of precipitate, and you can back calculate the concentration in the solution. Right? So you can also do it in the other way around. So that's always good to think about that. Okay, so this is enough for the precipitate. So let's go to the next type of reactions, which is acid-base reactions. So in the acid-base reaction, we always need a proton donor, which is the acid, and a proton acceptor, which is the base. And we often call this neutralization reactions because we have an acid which is neutralized by putting base in there. Essentially, this means that protons are reacting with the hydroxide ions to form water, which is neutral. And the hydroxide ion is a strong base, which means that when we put it into water, it will take the proton from water. So we will take hydroxide, put it into water, then we will actually get one of these protons from water, and then the other one will become hydroxide. Well, this one, now you have the same reactants on both sides, so it will be like equal in both directions, right? You have the same amount of both directions. But you could have something else here, which has a tendency to lose protons. For example, you could put HCl here. And then this will lose the proton, and you will form Cl-. So now this reaction would be very much on the right side. And at the core, what is happening here is just this one. We react this one with the proton to form water. This is what is underlying here, because HCl is a strong acid. So HCl will also fully dissociate into the protons and the chloride ions. right? So in the solution, when you have HCl, you have only protons and chloride ions, right? Now, essentially, the protons can react with the hydroxide to form water, and the chloride will be just the spectator of the reaction. So what I want to say with this is, so when you have a strong acid and a strong base, that at the core you always have this reaction in the solution. Because strong acid and strong base is fully dissociated, right? So let me give you another example for this. So let's say you put like sodium hydroxide together with HCl. Let's take a liquid here. And then the question is what will happen. So you can write down the ions here because all of them are fully dissociated. So once you put them in the solution, they will fully dissociate into protons and hydroxide. Now you can see what will happen. These here will just come together. And they will form water. So you are left with sodium and chloride and water. Right? And now you can also see this would be now again this complete ionic equation. And if we want to get the net equation, then the net equation will be simply this one, right? Okay, so for the strong acid and strong base, we always have reactions of protons and hydroxide in the solution. So we can do a couple of examples for how to calculate this now. So this is also the strategy they suggest here. We list the species first that are in the combined solution before the reaction. Then we write down the net ionic equation. And then we calculate the moles of reactants. For reactions in solution, we use the volumes and to convert to the moles with the concentration. Again, determine limiting reactant, and then we can calculate moles and mass of the product. Okay, in a certain experiment, 28 milliliter of 0.25 molar sulfur acid nitric acid and 53 milliliter of 0.32 molar of potassium hydroxide are mixed. What is the concentration of proton and hydroxide ions in excess after the reaction goes to completion? Okay, so what we just said is that, well, you have volume and concentration, so you can convert to mole number, right? And what we also know is that these are both strong acid and strong base, so they will fully dissociate into the solution. And the chemical reaction will just be the proton reacting with the hydroxide. Okay, so before that we have all these ions in the solution, but the net ionic equation will be just proton plus hydroxide reacting to water. We calculate the moles using the concentration and volume for both cases. What is the limiting reactant? Protons, right, concentration is smaller than the hydroxide, and we always need one proton for one hydroxide, right? So the limiting reactant would be the protons. And then, so we need to determine the amount of hydroxide that will react. It will be exactly the amount of protons. So what is remaining in the solution is the difference between the original amount of hydroxide minus the amount that is consumed. So the original amount was 1.7 times 10 to the power minus 2 mole, and we consumed 7 millimole by reaction with the protons. And then we are left with 10 millimole of hydroxide. Okay, and then we can take this and divide it by the total volume of the solution. So we need to combine the volume of the nitric acid and the hydroxide solutions. This will be, total volume will be 81 milliliter. And then we divide by this to get the concentration, which is then 0.123 mole per liter. So a neutral solution is a solution which has no hydroxide or protons in excess. Yeah? So this would be an example of a basic solution which has excess in the hydroxide ions. So maybe write this here. Okay. So now this brings us actually to a topic that is quite useful in practice, because what you maybe realize is here that, well, if we do these reactions, these quantitative reactions, which are complete reactions of acids and base, then we have a way actually to back calculate the concentration of the solution. Because if we know the concentration in excess after the reaction, we can actually refer back to the original concentration in the solution. This is similar to what I just explained you with the precipitate. We measure the mass of precipitate and we can kind of back calculate what was the concentration in solution. So this technique is usually called titration. So we usually use that to determine the concentration of the solution or the amount of substance in a certain volume. So the idea is that we deliver a measured volume of a titrant into a solution, which is an analyte. So the titrant has usually a known concentration, and the analyte, we don't know the concentration. And the only thing that we need to find out is what is the point where the mole numbers are exactly matching with each other, so that we have a quantitative reaction, we have no excess in hydroxide or proton. And in order to measure that point, so we need to measure this neutral point here. In order to measure this, we use an indicator. Indicator is a molecule which switches its color based on the concentration of protons in the solution. Yeah. So this is usually a weak acid or a weak base. So when we put it into some acidic solution, it will to some degree convert to the other product, which is an indicator with a proton added to it, or indicator minus a proton. And the indicator end is this is the indicator. So let's say we add proton to this, we react this to the indicator plus just the indicator with the proton added to it. And this will usually be a weak acid, so we will draw the both arrows. This is just to indicate that we will have a mixture of these two. And this will have a color 1, and this will have a color 2. And the transition, the transition from more of this to more of this will depend on the proton concentration. The more protons you have, the more you will move this to the indicator H+. So the color will depend on the concentration of protons. So that's the idea of the indicator. So you can mark the equivalence point where the concentrations of protons and hydroxide are exactly equal to each other. Yeah. So this is usually called the equivalence point. So the neutral point doesn't necessarily mean that the concentrations are equal. In this specific case, it means that, but in general, equivalence point is generally defined as NOH minus equals NH plus. So the amount of hydroxide we added and protons are exactly equal. That's the equivalence point. For this specific case, this also means it's neutral. But this doesn't need to be, actually I should put N in it, C, or I mean concentrations after adding together, but maybe to be more accurate, I'll just write N here. So for this specific case, it means the same thing. But we will see that in the case of weak acids, those 2 points are not the same. Yeah. Okay. So what do you need to know when you do titration? What is important? Well, there's an exact reaction between the titrant and analyzed, and you have to know that reaction, right? And this reaction has to be rapid and complete. Yeah, and it's also possible that it's incomplete, but then it's more complicated, and you have to know a little bit more. So the easiest thing for titration is if both reactions are complete. Yeah? If the reaction of this full reaction is complete, then you can easily calculate this. And then the stoichiometric or equivalence point, you can mark this one accurately once you have the indicator that switches color at that point. And the volume of titrant required to reach the stoichiometric point, you have to be able to measure that accurately. So if that is all satisfied, then you can do the titration. One of the indicators that you can also use then is phenolphthalein. It's colorless in acidic solution and pink in the basic solution. Okay, so this will be here then colorless and pink here. So once you add protons to it, it will be colorless and pink here. And it remains colorless when acid is titrated with the base until after the acid is consumed and the first drop of excess base is added. So this is actually the important thing for indicator. They don't switch the color continuously, but they switch it very abruptly and very suddenly, so that you can very accurately measure the point, the equivalence point. And the end point of the titration is when you add like 1 drop of the additional base, and suddenly the color, you see the color form, right? That's the point where you have exactly converted, where you are exactly converting this to this, and then the color changes. So this is showing this. So you are at the end point, and you add 1 more drop, and now you have basically this conversion of the indicator, which tells you that you reached the concentration of protons in solution that is exactly matching the point where this equilibrium here is switching. Okay. One example for this, a student carries out an experiment to standardize, which means determine the concentration of a sodium hydroxide solution. For this, he weighs out a 1.3009 gram sample of potassium hydrogen phthalate, KHP. And KHP has only 1 acidic hydrogen that can be donated. Molar mass is given here. And the student then dissolves this in the distilled water and adds phenolphthalein as an indicator. And he titrates the solution with a sodium hydroxide solution. So you have a strong acid and a strong base. A strong acid is this KHP, which concentration you want to determine. and you have the sodium hydroxide, which you are adding to it. And the phenolphthalein has the property that it switches color exactly when the neutral point is reached. So exactly when the numbers of protons and hydroxide that are combined in the solution are exactly equal, then the phenolphthalein will switch the color. So that is the special property about it. There are other indicators which switch at other values of this balance. So there are indicators which switch if you have double the amount of hydroxide compared to protons. There are also indicators like that. So totally depends on the form of indicator you use. Okay, so the difference between the final and initial Burette readings indicates that you used 41.2 milliliter of sodium hydroxide to reach the equivalence point. And so this is the point where you react all the 1.3009 gram of KHP. Okay, so you have measured the volume that you need to neutralize the solution. Now you just need to calculate from this the concentration. Okay, so how do we do this? Well, we write down the equation first. We have the KHP reacting with hydroxide. KHP donates the proton and to hydroxide to form water. It's a complete reaction. It's a strong base and a strong acid. And then what we do is we write the net balanced equation here. And then we calculate the moles of KHP. We know the mass that we weighted, and we know the molar mass. So we have 6.37 millimoles of KHP. And now we can calculate the limiting reactant. For this, we require the addition of enough hydroxide to exactly cancel KHP, which means it's a quantitative reaction and we don't need to concern with that. That's the idea of titration, that we exactly reach the point where we have a quantitative stoichiometric reaction, so nothing is limiting. And what are the moles of hydroxide required? Well, we need exactly the same amount, right? So we had 6.37 millimoles of KHP. So we need exactly the same amount of hydroxide to neutralize. So the molarity of the sodium hydroxide solution is given like this. So we used 6.37 millimoles by the volume divided. So the concentration of sodium hydroxide is 0.1546 mole per liter. Okay, so this is now a very accurate number for this concentration. So you can write this on the flask, you can put it in your desk. This will be the standardized solution. And if you want another one, you can dilute it with the strategy we discussed today. Right. Okay, I think we stop here. We continue with this topic next week. Okay? So until here will be the short test.